Our planet doesn't exist in isolation. It is part of a vast cosmic dance influenced by the gravitational forces of other celestial bodies. We are constantly being tugged and pulled by celestial bodies, most notably the Sun and the Moon. These two have the most significant impact on our planet due to their relative proximity and size. Gravity is the force that draws objects with mass towards each other. It is a fundamental force of nature that governs the motion of planets, stars, and galaxies. The Sun, with its massive size, exerts a strong gravitational pull on Earth, keeping us in orbit. This gravitational bond ensures that Earth follows a stable path around the Sun, providing the conditions necessary for life. The Moon, though smaller, also exerts its own gravitational force. Its influence is most noticeable in the way it affects our planet's tides. This constant interplay of gravitational forces influences many phenomena on Earth, including the tides. The gravitational pull of the Moon causes the water in our oceans to bulge out in the direction of the Moon. These gravitational forces are not uniform across Earth's surface. Variations in the Earth's topography and the distribution of mass within the planet cause differences in gravitational strength. The side of Earth facing the Moon experiences a stronger pull than the side facing away. This differential in gravitational force creates two tidal bulges on opposite sides of the planet. This difference in gravitational pull creates a bulge in Earth's oceans, leading to high tides. Coastal areas experience these high tides as the water level rises significantly. Conversely, areas experiencing weaker gravitational pull experience low tides. During low tide, the water recedes, exposing more of the shoreline. This constant push and pull of gravity from the Sun and Moon isn't limited to our oceans. It extends to the entire planet, affecting various aspects of Earth's environment. It also affects Earth's crust, though these changes are much subtler. The gravitational forces can cause slight shifts in the Earth's crust, contributing to geological activity over long periods. Understanding gravity's pull on Earth helps us appreciate the delicate balance that sustains life on our planet. It is a reminder of our connection to the cosmos and the forces that shape our world. As we continue to explore space, the study of gravitational forces remains crucial. It not only helps us understand our own planet better, but also the dynamics of other celestial bodies in the universe. Gravity is the invisible thread that weaves the fabric of the cosmos, binding everything together in a harmonious dance. It is a force that, while invisible, has a profound impact on our daily lives and the very existence of our planet. So the next time you look up at the night sky, remember the unseen forces at play, shaping the world we live in and the universe beyond.
We often associate tides with the ocean, and rightfully so. The rhythmic rise and fall of sea levels are a direct result of the Moon's gravitational pull. This celestial dance between the Earth and the Moon creates the mesmerizing ebb and flow we witness along coastlines around the world. The Moon's gravitational pull is the primary driver of these daily rises and falls in sea level. As the Moon orbits our planet, its gravitational force pulls on the Earth's oceans, causing the water to bulge outwards. This results in high tides in the areas directly facing and opposite the Moon, while low tides occur in the areas perpendicular to the Moon's position. But the Moon's influence extends beyond our oceans. Its gravitational pull also affects the Earth's solid surface, causing subtle shifts and movements that are not as easily observed as the ocean tides. Its gravitational pull also affects Earth's solid surface, albeit to a much lesser extent. These movements are so slight that they often go unnoticed, but they are a testament to the Moon's far-reaching influence on our planet. These subtle bulges in Earth's crust are known as Earth tides or terrestrial tides. Just like the ocean tides, Earth tides are a result of the gravitational forces exerted by the Moon, causing the Earth's crust to flex and bulge slightly. While Earth tides themselves don't directly cause earthquakes, they do create stress within Earth's crust. This stress can accumulate over time, contributing to the overall tectonic activity of our planet. Imagine someone constantly squeezing and releasing a stress ball. The ball might not break immediately, but the constant pressure weakens it over time. This analogy helps us understand how the continuous stress from Earth tides can impact the Earth's crust. The ball might not break immediately, but the constant pressure weakens it over time. Similarly, The Earth's crust experiences ongoing stress from these tidal forces, which can weaken fault lines and make them more susceptible to movement. Similarly, these tidal stresses can contribute to the buildup of pressure along fault lines, the zones where Earth's tectonic plates meet. Over time, this pressure can lead to the release of energy in the form of earthquakes, reshaping the landscape and reminding us of the dynamic nature of our planet.
The Sun, our life-giving star, is not always as calm and predictable as it appears. It occasionally throws tantrums in the form of solar flares and coronal mass ejections, or CMEs, collectively known as solar storms. These events release massive bursts of energy and charged particles into space, some of which are directed towards Earth. When these charged particles from solar storms interact with Earth's magnetic field, they can cause geomagnetic storms. These storms can disrupt satellites, communication systems, and even power grids. The energy from these storms can also interact with Earth's ionosphere, the electrically charged layer of our upper atmosphere. The Sun operates on an 11-year cycle known as the solar cycle, characterized by periods of high and low activity. This cycle is marked by the rise and fall of sunspots, solar flares, and coronal mass ejections, or EMEs. These phenomena are not just spectacular to observe, but have profound effects on space weather and, intriguingly, on Earth itself. During solar maximum, the Sun is more prone to solar flares and CMEs, which are massive bursts of solar wind and magnetic fields rising above the solar corona or being released into space. These events can disrupt satellite communications, power grids, and even pose risks to astronauts in space. Conversely, during solar minimum, the Sun's activity diminishes significantly. The number of sunspots decreases and the Sun's surface appears much calmer. This period of reduced activity can last for several years, providing a stark contrast to the bustling solar maximum. Scientists have observed a correlation between the solar cycle and earthquake frequency. This observation has led to numerous studies aiming to understand the underlying mechanisms that might link solar activity to seismic events on Earth. Studies have shown that during solar maximum, when the Sun is most active, the frequency of earthquakes tends to increase. This pattern is particularly noticeable in regions that are already seismically active, suggesting that solar activity might act as a trigger for these natural events, particularly in seismically active regions. These areas, already under stress from tectonic forces, might be more susceptible to the additional energy input from solar activity, leading to an increased likelihood of earthquakes. This suggests a potential link between increased solar activity and the triggering of earthquakes. The exact nature of this link is still a subject of ongoing research, with scientists exploring various hypotheses, including the impact of solar-induced geomagnetic storms on Earth's crust. However, the exact mechanisms by which this might happen are still being investigated. Researchers are using advanced simulation equipment and data analysis techniques to unravel this complex relationship, hoping to one day predict and mitigate the impacts of solar activity on our planet.
Earth's magnetic shield is like a guardian against solar winds. This protective magnetic field is generated by its molten iron core. We call this magnetic field the magnetosphere. It acts as a shield against the constant stream of charged particles coming from the Sun, which we know as the solar wind. The magnetosphere, you see, deflects most of the solar wind. This is crucial because it prevents the solar wind from stripping away our atmosphere. But during intense solar storms, the pressure from the solar wind can, compress the magnetosphere. This causes it to fluctuate and interact with Earth's upper atmosphere. Deep within Earth's crust, rocks are under immense pressure. When subjected to stress, certain types of rocks exhibit a peculiar property known as the piezoelectric effect. They generate an electrical charge when squeezed or compressed. This effect is reversible, meaning that applying an electric field to these rocks can cause them to deform or change shape. While the piezoelectric effect alone may not be sufficient to trigger a major earthquake, it could potentially play a role in triggering smaller tremors or influencing the timing of earthquakes in already stressed fault zones. The devastating 2011 Tohoku earthquake in Japan, which triggered a massive tsunami, provides a compelling case study for the potential influence of celestial bodies on seismic events. Research suggests that the tidal stresses from a full moon, which occurred just days before the earthquake, may have contributed to the triggering of this massive earthquake. The Tohoku earthquake serves as a stark reminder of the interconnectedness of Earth and its cosmic surroundings. While the exact mechanisms by which celestial bodies influence earthquakes are still being studied, the Tohoku event highlights the need for further research in this area.
The Global Positioning System, or GPS, has become ubiquitous, used for navigation, tracking, and even social media check-ins. But GPS technology also holds promise for earthquake prediction. By monitoring subtle changes in Earth's ionosphere, the electrically charged layer of our upper atmosphere, scientists can potentially detect precursors to earthquakes. When an earthquake occurs, it can generate acoustic waves that travel upwards through the atmosphere, disturbing the ionosphere. These disturbances can be detected by GPS satellites as changes in the signals they receive. By analyzing these changes, scientists hope to develop early warning systems for earthquakes.
Earthquakes are natural phenomena that can have devastating consequences. While we cannot prevent them, understanding the factors that contribute to their occurrence is crucial for mitigating their impacts. Monitoring celestial activity, particularly solar storms and geomagnetic fluctuations, could provide valuable insights into earthquake prediction. By combining data from space weather observations, ground-based seismic monitoring, and advanced technologies like GPS, we can enhance our ability to forecast earthquakes, potentially saving lives and property. As we delve deeper into the cosmos, we gain a greater understanding of our own planet and the intricate ways in which it interacts with its celestial neighbors.